Hello and welcome to this MCMA webinar, Ethernet or EtherCAT for Motion Control, choosing the right network for your applications. My name is Joanna Keel and I am the Manager of Marketing and Membership for the MCMA, and I'll be serving as your moderator. Attendees that have joined this webinar today have joined in listen-only mode, which means that you are muted. If you do have a question during this webinar, please submit them in your questions panel of your webinar screen, and we will answer all questions after the webinar has concluded. This webinar will be recorded and a link will be sent to you within the next 24 hours. And now I'd like to introduce our presenter for today's webinar, Matt Clint. Matt has joined Galil in 2013 as an applications engineer. Before coming to Galil, he worked as a development engineer in the physics department at UC Davis, where he was involved in developing hardware and software solutions for experiments in condensed matter and astrophysics. Matt has brought this expertise to Galil and has worked with numerous research institutions on motion control and data collection projects. At Galil, he worked closely with other application engineers in R&D development of Galil's EtherCAT compatible controllers. Matt holds a bachelor's in physics from the University of California at Davis. And now I'd like to thank our exclusive sponsors of today's webinar. Electromate. Electromate is a co-sponsor of today's webinar and the exclusive Canadian distributor for Galil Motion Control. Electromate's core purpose is to help manufacturers build better machines using differentiated automation technology. They specialize in robotic and mechatronic solutions for the industrial automation marketplace. Respected by customers as a premier source of high-performance automation and motion control components and systems, Electromate specializes in servo and stepper motors and drives, motion and automation controllers, positioning systems and actuators, feedback devices, gearing products, and operator displays, all supported by via extensive product selection, just-in-time inventory, dedicated to customer service and technical engineering support. Galil Motion Control. With over 750,000 controllers sold, Galil is the leading manufacturer of motion controllers and PLCs. Since the introduction of the first microprocessor-based motion controller in 1983, Galil has remained one of the industry's leading innovators by offering its customers powerful, cost-effective, and easy-to-use motion controllers and PLCs. Galil is committed to being your primary source for any motion control and I/O application. Galil motion controllers and PLCs are backed by superior technical support and can accommodate the most demanding applications with absolute precision. And now I'd like to hand it over to Matt to begin.
Thank you, Joanna, and welcome everyone to EtherCAT or Ethernet for Motion Control. As Joanna mentioned, my name is Matt. I'll be presenting today. Been with Galil Motion Control for about 2 years now, and I've been integrally involved in the development of Galil's EtherCAT hardware. So today I'd like to spend a little time talking about Ethernet and EtherCAT, the differences between them, and attempt to answer one of the questions we get most often here at the applications department at Galil, which is better, is what we hear quite a bit. After that, I'd like to introduce the Galil DMC 50000 EtherCAT Master and our recently released remote EtherCAT I/O module, and then also show some examples of using that hardware in an EtherCAT network. And finally, summarize cost benefits of either EtherCAT or Ethernet for your application. So first, a little bit more about Galil. Joanna gave a great summary there. So founded in 1983 by Dr. Jacob Tal and Wayne Barron, first microprocessor-based servo controller, and we've been profitable for over 120 consecutive quarters. As a matter of fact, that slide might be slightly outdated. I think it's 122 now. 750,000 motion controllers and PLCs delivered, and really what we pride ourselves on, really one of our selling points is the engineering support. I'm slightly biased being an applications engineer, but we really do enjoy working with customers to find solutions to their applications needs, as opposed to walking them through the manual or things of that nature. And so really as a group, our focus is to work with OEM customers offer the most cost-effective solution to their motion control needs. And that being said, if you can't find a controller or PLC to meet your requirements, we really do work with quite a few customers on custom firmware and hardware solutions for their applications. So Ethernet and EtherCAT can be a pretty broad subject, and so the first thing I would like to do is drill it down to specifically how it pertains to motion control in particular. And so before we do that, let's just establish a little context, a little background. And so here we have a diagram of just a standard motion control system where you have a motor and encoder turning a load of some type in a machine. The motion controller is generating a command position that is then translated into a control signal that has been formed from position feedback from the motor. So the overarching principle of the system is you have the motion controller is watching the motor and encoder, essentially watching that position, comparing it to where it needs to be, and then producing a command signal or control signal that then powers the motor and amplifier to minimize that error. And for decades, the hardware standard has been, and will continue to be, an analog voltage being the control signal between the controller and amplifier, typically plus minus 10 volts for servo control. And then digital feedback from the encoder, standard quadrature or absolute serial encoders. And the real benefits of that is it's an established technology. It's been around for decades. Most control systems engineers are going to be very familiar with it. Low cost. It's been around so long that there's a multitude of vendors offering pretty much everything under the sun for pretty competitive pricing. And the system has very little latency. Your control signal at your motion controller is a voltage, simply a voltage that's being generated that the amplifier then sees and turns into a current that goes through the motor coils. And then the feedback from the encoder, again, is just a voltage seen almost instantaneously at the motion controller inputs. And so there's no latency in the system. There's no a chance for race conditions or for information to get mixed up, essentially. Some of the downsides to this control scheme: analog signals are much more susceptible to noise than digital signals. However, even digital encoder signals can fall victim to noise in extreme cases, where you have, an application, say with plasma cutters, for instance. You have large amounts of electromagnetic interference, can cause false triggering and false encoder counts. Wiring between multiple components, the controller to the amplifier to the motor, encoder to controller, and back as well, now you've just got a bundle of wires running back and forth, and each one of those is a potential increased risk of failure. Another wire that can break, another wire that can get noise on the line, as well as the fact that in order for this system to work, every component they all have to share common ground, and in some cases that introduces additional complexity in terms of ground loops and appropriate grounding schemes. This becomes especially problematic if the motor amplifier and motor need to be physically separate from the controller, over large distance, 50, 100 feet or more. The longer that those analog signals travel, the more susceptible to noise they are. And lastly, changing components, changing out a drive is slightly complex in that in order to do so, you need to make sure that the new drive's internal circuitry is compatible with the old drive, essentially, so that the command signals and encoder signals that are being taken in and put out are comparable, so that the controller can interpret and command it appropriately. On the other side of it, we have digital control schemes. There's varying protocols: TCP/IP, RS-485, Modbus, DeviceNet, and EtherCAT. The benefits is that one of the main benefits is that communication over Ethernet has become fast enough, over 100 megabit per second now, to make these types of communication what we call virtually deterministic, meaning that for all intents and purposes, you can ignore the communication latency in most applications. These wiring schemes make them very easily upgradable. It's a standard Cat5 Ethernet cable. So if you're going to remove one drive, plug another drive in, you just plug the Cat5 cable in, as opposed to motor command lines and grounds and encoders and all of that good stuff. And digital systems are a lot less prone to typical Ethernet signaling protocol. It's a differential signal with twisted pair wires, making it extremely noise immune. Remember that Ethernet cables are used in office buildings all over the world for internet communication, and as such are pretty robust. Downsides is that each node, so let's say each amplifier and motor combination or I/O module at the end of this communication is going to be costlier than a standard analog amplifier, because you have the amplifier and I/O hardware, plus there's a dedicated microcontroller on each one of these nodes whose sole purpose is to take this communication and parse it into necessary motion commands, motion data. And so there is increased cost associated with that. The other major downside to these protocols is latency. In order for that information to get from the controller to whatever node it needs to go to, the controller needs to produce the data, wrap it up in an appropriate packet that matches the protocol, then send down the line, and then the node on the other side needs to take that data, unwrap it, and route it appropriately. And this is non-negligible time for the purposes of motion control. So now we'll go into two of the main control system layouts, one being centralized, the other distributed control schemes. In centralized control, typically analog control signals are still predominantly used. The operative word with centralized control is coordinated, specifically coordinated motion, coupled motion, these kinds of terms. I'll probably be saying it many times. And can be, some examples are a CNC machine, diagnostics machines, semiconductor pick-and-place robots. Typically machines where everything is in the same box. You have, say, XYZ axes, a couple of actuators. Let's see. So it sounds like we're seeing somebody is having some difficulty with the slide. Let's see.
I think we're good now.
Okay.
Thanks, Matt.
Sure. So having everything in that central location makes the extended wiring of an analog system much simpler to deal with, and also less susceptible to noise, because typically they're, for lack of a better term, all wrapped in a big metal box and shielded from external EMI. And again, the only, since everything is physically close, is all analog, and these low-level digital signals, the latency is low. So that, again, that keyword coordination, you can coordinate I/O to motion. A couple examples being, say, a CNC lathe, and when you first bring the lathe up, the system has to be homed, so it has to know where it is. In order for the homing to be accurate, the controller needs to know exactly when that home sensor was tripped during a move. Now, when I say exactly, I mean within fractions of a second, a few milliseconds or 100 microseconds. And that's the kind of timing that you're only going to get if all of the I/O and motion control hardware and algorithms are all on the same controller, all on the same hardware. Right. So this is all well and good for a centralized system. However, once that system starts to get bigger, now instead of a CNC machine, say the size of a clock, now you're building a plasma cutter that is, say, cutting the bed for a locomotive. So you're cutting out pieces of steel that are 80 feet long, 20 feet wide, and so those analog signals are now moving over quite a bit of cabling and next to some pretty high noise sources. So that's where we come into the distributed control idea. Then the distributed control, the operative term would be the left hand doesn't know what the right is doing. You have a central control system, or say watch room, something very similar to plant monitoring. You have an operator sitting there looking at all these screens, buttons, dials, monitoring everything going on in a plant, say. So one master control node oversees the actions of all slave nodes. Those nodes can be motion controllers, PLCs, temperature sensors, any number of devices. Master sends commands that gather data from different nodes, and then based on that data, we'll send out commands to other nodes on the system. Again, a simple transaction could be a PLC sees a transition on a bit that indicates, a temperature threshold has been exceeded, and so that information is sent back to the central, the control center, which then sends out a packet or information to a motion controller, says open this motor so that the temperature can drop. So as you can see, that is a much more loosely coupled control than a centralized system. And one of the main problems with a distributed control system is that lack of coordination, of determinism, really. In the case, and really where it's introduced is in that communication. The amount of time that it takes the data to be wrapped up on the PLC, sent to the control center, a decision is made, data is wrapped up again, sent to the actuator, unwrapped and acted on. That time may be minimal, but it's also it's unpredictable. And that really begins to be a problem if you're trying to tightly coordinate motion on a distributed control network. And that's where we come into EtherCAT and Ethernet. Typically, Ethernet is used in analog control systems in order for either a host PC or HMI to communicate with a motion controller. That motion controller then sends as we discussed, analog commands, taking in digital feedback, and there can also be additional nodes involved with Ethernet, but the communication between them is not coordinated. But Ethernet is designed to move large amounts of data through many different nodes, able to route data to and from billions of separate addresses, allowing communication over vast networks like the internet. Ethernet communication is what the internet uses to move pretty much everything. However, all of this flexibility incurs a large overhead involved in wrapping that data up and routing it. So not only does your Ethernet packet have an address attached to it, it's got a protocol attached. So basically, where is it going? How is it supposed to be read? And how is it supposed to be responded to? There's a lot of overhead in processing that data. EtherCAT uses standard Ethernet hardware, so good old Cat5 cabling and network interface cards. However, EtherCAT, what's been done with EtherCAT is it's for lack of a better term, a stripped down version of Ethernet. It removes most of the flexibility in terms of types of data that can be moved back and forth, but it comes with the benefit of streamlined communication that provides that deterministic coupled motion that we were looking for from a centralized system, and allows you to put it into a distributed system. And this is done again by stripping out most of the data that comes on in an Ethernet packet. There's also hardware implementation via FPGAs or ASICs that moves that data through pretty quickly. However, all this coordination does require setup and configuration. So really quickly, we can go through the difference between the bits and bytes of Ethernet versus EtherCAT. So in this image, we have a standard Ethernet frame known as a packet. The first 6 bytes is an address. It's called a MAC address, and then a source address. So where is it coming from? Where is it going? And the ether type specifies which protocol. In this case, IP version 4, which is what the majority of data on the internet is sent as. And then the Ethernet data, that's the meat of the packet, but the actual data that's being sent. And then the CRC, which is a checksum at the end for data validation. If the CRC doesn't check out on both sides, typically the data is retransmitted until it's confirmed. So in an Ethernet system, and again, this would be a centralized control scheme. You would have a host PC or HMI communicating over Ethernet to the motion controller. And so the communication between them is over Ethernet, and because it is Ethernet, again, there is that larger overhead which can produce some non-determinants in the communication between them. However, the communication between the motion controller and drives is, for all intents and purposes, instantaneous, as we discussed, because they are those analog and low-level digital signals. EtherCAT communication, quick overview. So based on CAN open, specifically COE or CAN over EtherCAT, uses, again, standard Cat5 cabling and FPGAs for fast data processing. Multiple modes of operation, meaning that drives can be, currently the EtherCAT standard supports 6 different modes of operation, 2 of which are supported by the Galil DMC 50,000. We'll cover those a bit later. In addition to the hardware means of speeding up communication, as we said, the data formatting has to be configured prior to operation. And as you can see in the animation there, so you have your master sends out essentially the packet moving back and forth. Each section of the packet is dedicated to one of the slave devices. And the configuration before that network is essentially the master telling each slave, this is where you will look in the packet. So start at this bit and stop at that bit. Look at this portion of the packet, and that's the data that's yours to act on. Everything else, ignore it. Just send it on through. This is in contrast to Ethernet, where that data would come into the first slave drive. The data would be parsed, taken apart. The drive would then figure out what's for me, package the rest up, send it down the line. That processing, it takes a non-zero time. However, in this setup where the slaves know what data is where and what they need to do with it, there's a lot less interpretation, a lot less processing time taken. And one of the real boons of EtherCAT for achieving that kind of coordination is the distributed clock feature. Essentially, any time an EtherCAT network is brought up, the EtherCAT master will ping all drives on the network and calculate down to nanosecond resolution what the latency on the line is. So literally the amount of time it takes a packet to get from the master to the first slave, to the second, to the third, to the fourth. And then the distributed clock specifically keeps them offsets the motion commands for all drives appropriately, so that if it takes longer for the packet to get to slave 4 than slave 1 will offset its clock so that it waits that extra time before beginning motion. And so you really start to see coupled coordinated motion on the same level as typical Ethernet and analog control systems. A quick view of EtherCAT versus Ethernet, and you can already see from here that the EtherCAT packet is a lot more structured. You have the Ethernet header. Again, because the data isn't unlike Ethernet, where the data is, as we've shown, there's a 6-byte source and destination address. An EtherCAT master broadcasts the information to anyone who's listening on the network. However, because the network has been configured, the slaves that are on the network will only look at that part of the packet that they've been assigned to. So we take out the address right away. That's a whole chunk of bytes we don't have to worry about right there. The EtherCAT header is some preambles and how do you do's, specifying how the data is to be interpreted. EtherCAT data, that's again the meat of the packet and what's being sent specifically. In one case, the master will simply tell the drive what position I want you to be in encoder counts. What's your I/O status, and what's the drive status? So are there any errors on the drives? And so that's literally 12 bytes that are being sent down the line. And those are the only 12 bytes that slave is concerned with. And then that packet will contain that bit of information for each drive. And so an EtherCAT network layout as opposed to the Ethernet. So you can see you still have standard Cat5 Ethernet cable between them. The drives are daisy-chained. Each EtherCAT drive will come with 2 RJ45 jacks that act as EtherCAT switches, essentially. It's important to note that although Cat5 cabling and network interface cards are compatible with EtherCAT, standard Ethernet hubs and switches are not. And that comes down to the fact that I'd mentioned before, that there are no specific addresses in an EtherCAT packet. And so routers and switches specifically look at addresses to figure out where to route that information. And so if it doesn't see one, system doesn't do well with that. So as we can see, the EtherCAT master daisy chained to the first 3 drives. Now it's important to mention that even though the communication between the master and the drives is over Ethernet cable through the EtherCAT protocol, the communication between the drive and the motor and the encoder is still the analog control signal as well as digital encoder feedback. However, we get around the noise issue because that wiring is going to get a lot shorter. So in this case, in this network layout, each one of these EtherCAT drives could be up to 50 meters apart from each other. And then the control signals and encoder signals could be no more than a few feet away from the drive. So no matter how noisy the environment is, your EtherCAT solution is going to be a lot more robust in those types of environments because of the shorter analog wiring. And we can see at the end of there, the I/O module is also tacked on at the end of the network. So with the EtherCAT network, typically that coordination takes quite a bit of effort on the side of the EtherCAT master, and in terms of setting up the timing, setting up the individual packets that need to be sent back and forth, interpreting them. There's quite a bit of preamble that needs to be done. And this can be done through a number of software packages by the user. However, those can take quite a bit of working knowledge of how EtherCAT works, certainly beyond the scope of the kind of the broad range of this webinar. However, one of the primary benefits of, as we see here, the DMC 50,000 is that all of that coordination is taken care of in firmware. We've done extensive testing here with numerous EtherCAT drives, and our controller firmware specifically will coordinate a network to work with individual drives, making it pretty much transparent to the user. So some of the benefits of the 50,000 includes all the features of our latest generation DMC 4000 series, but adds the capabilities to run EtherCAT drives or networks with up to 8 drives and 2 I/O modules in cyclic synchronous position and torque modes. And we can discuss those a bit more. Position mode, as we mentioned in the previous EtherCAT frame, the master will send out a 32-bit number. It's an encoder position that the controller wants the drive to be at by the next cycle. And then in torque mode, that 32-bit number, instead of being a position, is now a commanded torque on the motor, so the drive now takes that number and translates into a torque to put on the motor instead. The main difference between those two modes from the Galil standpoint, in position mode, all of the PID tuning is done on each drive. In torque mode, the PID tuning is done on the Galil. The EtherCAT 50,000 master is the only motion controller in the industry with the ability to mix and match local and EtherCAT drive. The 50,080, for instance, can be configured with up to 4 axes of local control, so standard analog control signals and encoder feedback, and up to 8 EtherCAT drives. And those can be swapped out at any time. Your A axis can be a local drive, and with a couple commands you can switch it to an EtherCAT axis. And our main drive with this EtherCAT master is easy configuration and compatibility and flexibility. Really, it's based on our pre-existing command set. There's 3 or 4 commands that are added to standard DMC code that allows you to essentially plug in an EtherCAT drive and be up and running instead of a local axis. Our newest release, the Rio 57,000, is our essentially general EtherCAT I/O slave. Fully functional, meaning it's compatible with any standard EtherCAT master. It's back-off conformance tested, and supports distributed clock, which is essential when it comes to deterministic, on-time data sampling. And comes with programmable analog I/O ranges and field upgradable firmware, which again is pretty rare in the industry. Tracking down firmware for different vendors' hardware sometimes can be difficult, but we really do try to make it as easy as possible to track down. And every Rio comes with 16 high-powered 500 milliamp sourcing outputs, 16 digital inputs, and there's an option for 8 analog inputs and outputs. So a quick example of the difference between DMC code for a centralized control system and a distributed system using EtherCAT. As you can see on the left, the DMC command is needed to turn on the motor, command a motion, and then set a digital output. So you have servo here, position relative begin, after motion, set bit 1, and then MG will message that a move is complete out to the terminal. And then on the right, as you can see, I've taken the code that for a local axis and inserted it into another 8 commands. And the first few commands, the MT10 EX-1, and EU1 are all that is needed to bring up an EtherCAT drive. If you have an EtherCAT I/O module on the line as well, then you would use the I/O command. And so you can see that now the second chunk of code has been moved over. It's identical to a local drive. And then the last bit there is setting and clearing RIO, the EtherCAT remote I/O. So instead of set bit 1 for a local output, you would set bit 11,001 as per the addressing that's listed in our command reference. So if you have an existing application written on a Galil in DMC code, adding an EtherCAT drive would involve getting a 50,000 EtherCAT master and then adding these few commands, and you'd be up and running. And so given that flexibility of the 50,000, and given what we've spoken about the differences between centralized and distributed control, why choose? DMC 50,000 can accommodate a multitude of interfaces and buses, as we talked about EtherCAT. It also has a secondary Ethernet port, so it can communicate with your PC or an HMI. It can communicate over Ethernet through a standard Ethernet hub, and so you could have many 50,000s networked together in a distributed control system that then uses EtherCAT. The permutations get pretty they can get out of hand pretty quickly, which is good. It can match a number of applications. But the 50,000 can also communicate over TCP Modbus, RS-232, USB. There's a ton of options. And that really is one of the bright points. It is one of the only controllers on the market that allows that mix and match flexibility. And in addition to giving you the maximum amount of choice for what to use in your application, as we all know can happen if design considerations change later on down the line. If the budget was originally written for EtherCAT, but later on has been cut for some reason, analog drives are going to be easy to roll in because buying a 50,000 does not automatically lock you into either or EtherCAT or analog systems. So here's an example of a 50,000 essentially being used in mixed mode. You have, so pictured on the right are two servo motor standard amplifiers, two stepper drivers taking the standard step and direction lines, and those are local. So they're taking that analog signal, the digital encoder feedback, et cetera, et cetera. And then you also have the 50,000 wired into an EtherCAT network with 3 drives and a RIO 57,000. And so the local drives could be, sitting in the same CNC machine, let's say, and then the EtherCAT network, as we've talked about, could be distributed throughout the factory floor, doing well, who knows what. And again, because the 50,000 uses that, it all uses the same DMC code. Those drives, EtherCAT drives, are going to be transparent compared to the local drives. So at this point, Galil has 8 or 9 supported drives that we've worked with, that we've tested, that we've developed our firmware on. And we are actively looking for customers to roll new drives into our lineup. So like as it says here, if you see any devices here that aren't listed, please give us a call. We are more than willing to work with customers to roll in support for their selected drives. And we certainly welcome the opportunity. Any other questions about EtherCAT and whether or not it's appropriate for the application. We definitely want to be in on the ground floor with those discussions. So in summary, EtherCAT is getting a lot more lip service in the last 10 years. It's certainly becoming a more and more popular means of control. However, we'd like to stress that it isn't necessarily a cure-all. It is very good at what it does and in the applications for which it's appropriate. For quite some time, the standard analog control signal with transconductance amplifiers, quadrature encoder feedback, that's going to be an industry standard for quite some time, mainly because it's well understood, number one, and number two, it is going to be cheaper for quite some time. It'd be more cost effective. However, there are certain applications wherein the lower cost of those drives is going to be offset by the amount of trouble, essentially, that it takes to wire the system up and diagnose any potential noise on the system, anything like that. And so, in applications where tightly coupled motion over a distributed network, so two motors 50 meters apart from each other need to be moving in sync, essentially. That is really where EtherCAT is designed to be used. And although Ethernet control can't really technically be referred to as real time as EtherCAT is, because it is technically real time. For most applications, it is going to be close enough. The lag time in Ethernet communication is, if you're talking about moving large masses that aren't going to respond to commands more than once every few seconds, whether the message to move gets there in a millisecond or 5 milliseconds is not going to be an issue. And so, thank you for attending today. I hope you found this presentation insightful. And I'd like to thank our colleagues at Electromate for their support and assistance with the presentation. This time, I'd like to open up the presentation and take any questions that you have regarding EtherCAT or Galil. So again, thank you for joining us.
Great, thanks, Matt. Yeah, if you do have a question for Matt, go ahead and put that in your questions panel, and we'll try to get to it. If we don't get to all questions today, we will follow up via email after. So I have been keeping track. We've had quite a few come in, actually. So the first question I have for you, Matt, is comes from someone who says, I am already using one of the Galil Ethernet TCP IP-based controller for my 6-axis applications. Should I consider moving on to the EtherCAT-based controller?
Yeah, this is, like I mentioned, probably one of the most common questions we get from customers calling in about EtherCAT. And as always, the question is, what is the application exactly? If the application needs tightly coordinated motion or control over a large, physical footprint over a large distributed area, then EtherCAT may be appropriate. However, if you're building a 3-axis CNC machine, it's all going to be enclosed in the same box. There's really no advantage to using EtherCAT in a system like that. And so in that case, we would advise staying with the standard analog control and encoder feedback system as opposed to EtherCAT.
Great. Second question that came in, someone asked, my application uses a combination of electrical and hydraulic servos along with a couple of axes with step motors. How is this addressed by EtherCAT connectivity?
Okay. Well, it's somewhat similar to, if we go back to the analog analogy, if you any kind of servo drive that you have, if it takes the plus minus 10 volt servo command signal, then the actual amplifier or the motor size or the motor type that's being powered on the other side is completely invisible to the motion controller. And in the same way, EtherCAT, so if you're in position mode, so where the master is sending out that 32-bit position number, whatever drive is on the other side is going to look at that number and say, I need to move this many counts. And whether that be counts or steps, whatever it is, the motion essentially is going to be, or the type of hardware is going to be transparent to the EtherCAT master.
Thanks. Next question that we got from the audience is EtherCAT a deterministic or non-deterministic network, and which is better?
Again, the better question is pretty qualitative, but the short answer is yes, EtherCAT is a deterministic network, and EtherCAT is a deterministic network, and Ethernet is not. The determinism in a motion control system is typically laid out by the actual motion controller, and that boils down to the controller is working on a specified clock. And so no matter what it's doing, at that clock tick, it calculates the next position that a motor needs to be at, and it does that on a regular interval, and that's really what defines determinism. And the EtherCAT network shares that clock essentially, and allows for that deterministic control over large networks.
Great. Next question. How are local and remote I/O sampled in an EtherCAT distributed control system?
Very similarly to the way that position will be commanded on a drive, the EtherCAT master will send out what is essentially a blank packet, which the I/O module, and in our case would be the Rio 57000, sees that blank packet, and because of the way the EtherCAT network has been configured, knows that its I/O data needs to go in that space in the packet whenever it comes by. And so that packet comes in, the I/O module puts the data in, gets back to the master, and the master acts on it. And then, as soon as that's done, another packet comes around, and communication continues.
Thank you. Yeah, we're getting some questions. I think we still have time for 2 more to ask you, but again, if you do want to put them in your control panel, we will follow up via email. So the next question I've gotten from the audience is, can I use a wireless router and adapter in my motion control system with Ethernet and or EtherCAT?
One of the engineers I work with, he likes to put it as determinism and wireless don't go in the same sentence. The trouble with, well, first off, using EtherCAT with any of the standard Ethernet hubs, switches, anything like that, wireless or not, is a non-starter. However, the problem with determinism and wireless communication is that wireless, it's tough to diagnose if there are breakdowns in communications. If an EtherCAT master sends out a data packet to slaves over wireless and it doesn't get there, how did the slaves know that they were supposed to get something? And if they did know they were supposed to get something, now they have to signal back to the master and say, hey, I didn't get that data. The master has to resend it. At that point, the benefits of EtherCAT, the coordination and determinism have been lost, because now you don't know when that data is coming back and forth, and literally your motors are sitting there waiting to do something, waiting for instruction while your wireless signal pings around the building. In some cases, for Ethernet, some data collection I would say can be done over wireless, as long as the acquisition rate isn't too high. But again, even with Ethernet, when you introduce wireless communication, especially in the kind of environments where motion control is used, which are typically noisy industrial environments. Adding wireless to the system really, I think in most cases will add more complication than is worth it.
Thanks for that answer. Last question again that we're just going to get to in the live version, and all the rest will follow up via email. Are there plans for a 1 gig Ethernet or EtherCAT communication in the future?
Mm-hmm. Well, the standard for most motion controllers, and the 50,000 is no exception, and all of our current generation controllers, in that they share 100 megabit per second Ethernet communication bus, and EtherCAT communication also shares that specification. And at this point, for motion control, that's honestly more bandwidth than is needed at this point. The bottleneck really now is how quickly does the data need to be processed. You can certainly put gigahertz processors on your motion controllers and your EtherCAT drives, but we have to remember that these are controlling physical systems, and if your motor in your system has a bandwidth that can only respond to a command, say 50 or 100 times a second, there's really not much point in telling that motor to move 1,000 times a second. It's not going to be able to respond. And so at this point, there may be plans in the works somewhere for gigabit EtherCAT or Ethernet, but at this point, I think that the applications for which it would be appropriate would be few and far between.
Thank you, Matt. Yeah, we did, like I said, got a lot of questions, so I know a lot of you didn't get yours answered, but we will follow up with you via email after this webinar has concluded. I did want to stick to our timeline, so again, I wanted to thank you, Matt, and our participants today, as well as our sponsors, Electromate and Galil. And as a reminder, this webinar has been recorded, and a link to the recording will be sent to you within the next 24 hours. If you did have any questions, we will follow up via email after this webinar has concluded. And be sure to visit www.motioncontrolonline.org for a list of our upcoming webinars. Thank you, everyone, and have a great rest of your day.